Hello chemistry champions, this is Werner. Welcome to the channel where we solve chemistry problems. Today I want to talk about a proposed mechanism for the transformation of an oxime into an amide. This important chemical reaction is used in the synthesis of caprolactam, which is a precursor to nylon, and is used in the synthesis of plus codeine, amongst others. By the end of the video, you will be able to recognize this reaction in future and have a better idea what are the key chemical principles at play to make the reaction work so well. Let's have a look. Seasoned organic chemists will recognize the reaction we'll discuss today as a Beckmann rearrangement. And as the name suggests, it was discovered by the German chemist Ernst Beckmann in 1886, when he was only 33 years old. And I think that's a great age to discover a chemical reaction that will bear your name for centuries to come. The Beckmann rearrangement is an acid-catalyzed reaction that converts oximes derived from ketones or aldehydes into amides or lactams. Let's first talk about how oximes are made in the first place. Here we see a reaction where cyclohexanone is treated with hydroxylamine to form cyclohexane oxime. This oxime, by the way, can be further treated with sulfuric acid to form caprolactam, a critical monomer for the manufacture of nylon 6. Another way to make an oxime is through a cyano route, starting with a cyano derivative containing a methylene group and then reacting with sodium nitrite to form the corresponding cyanoxime. A complete set of compounds worthy of investigation are the cyanoximes in their own right. They are particularly popular among synthetic or inorganic chemists due to all the different donor atoms that can potentially be obtained and used as ligands. An oxime is the C double bond NOH portion of the molecule as shown here. Let's now move on to the actual mechanism. The first step in the Beckmann rearrangement is the protonation of the oxime oxygen, which leads to the cleavage of the NO bond, because water is a far better leaving group than the hydroxide ion. The difference between water and hydroxide ion as leaving groups is huge, and think no further than the conversion of a primary alcohol to the corresponding bromide, which occurs only in acidic media. That is, the reaction between a primary alcohol and a bromide produces no reaction, while the same reaction in acidic media protonates the hydroxy group, leading to the brominated product. And the same happens here. As the water departs from the compound B, a phenyl group migrates to form a transient species with two resonance contributing structures, C and D, designated by the double arrow. This step is probably the key feature of the entire reaction, which is a 1,2 shift or 1,2 migration of an alkyl group, or in this case an aryl group, from the carbon atom to the nitrogen atom of the oxime. The question then is between C and D, which is the more important? I would suggest D, because all its atoms have an octet of electrons, whereas on C, the carbon atom only has 6 electrons. Migration would occur with greater difficulty if not for the presence of an unshared pair of electrons on the nitrogen atom on C, which stabilizes the carbonium ion and the transition state leading to the carbonium ion. Experiments have shown that the phenyl group that migrates is the one trans to the water. Water that could come from the solvent attacks the cation to form E. Note that the water molecule attacks the carbon atom, not the nitrogen atom. Formation of an NO bond would not be expected because addition of the nitrogen would generate a tripolar species with adjacent positive charges, as shown in the bottom left. Equilibrium between E and F is much like that between water and the hydronium ion. The proton of E is lost to a solvent molecule or to a solute molecule, such as A. F is in equilibrium with G, the product, but it lies far to the right. The two species are in fact tautomers, a term referring to structural isomers in rapid equilibrium with each other. Notice the steps E to F to G involve only proton transfers. Proton transfers to and from nitrogen and oxygen are typically extremely fast reactions. A final interesting observation is that starting oxime A is actually protonated to a greater extent on the nitrogen than at the oxygen because amines are generally more basic than alcohols. But the protonation at the nitrogen is reversible and does not result in any further reaction. But the small yet finite amount of B formed in equilibrium with A in the acidic medium is what ultimately gives rise to the product. So, let's summarize here the 4 key steps of the mechanism. Number 1 is the protonation of the oxime oxygen, making it a better leaving group. Number 2 is the migration of the group that is anti or trans to the oxime hydroxyl, migrates from the carbon to the nitrogen. Number 3, cleavage of the NO bond, or the bond forming of the migrating group with nitrogen. And finally, water gets eliminated, leading to the formation of the amide. And that is one way to interpret a proposed mechanism involved in the Beckmann rearrangement. I hope you found it of value. Let me know in the comments if you think different mechanism interpretations are possible. Please also consider to subscribe to the channel for similar content. Stay curious, thanks for watching, and I hope to catch you in the next video.